I think we've got a couple of microphones that we could spread around, maybe one up the front and one down the back, and we'll see what questions we can get from the floor. While the microphones are coming out, I've got one to get started. We'll start with the first speaker, Fouad. You mentioned the challenges of implementing viscous dampers on bridges, very lively animals that like to move all the time. The San Francisco-Oakland Bay Bridge and Vincent Thomas both demonstrated long-term reliability challenges. And notably, not just one manufacturer, several manufacturers were involved. So this is let's say, a universal challenge for the devices. I was going to say I've got a question, but it's actually three questions. The first one is simple. How many years have the replacement dampers been installed? Secondly, have the design modifications been effective? Have the changes that were implemented to accommodate or mitigate the surface deformations been effective in protecting the dampers? And the last one is, what monitoring techniques or what systems have you implemented to keep an eye on the dampers into the future? Since the mic hasn't made it here, I'll give you mine. That'll stop me asking more questions.
So as far as how long it took, I mean, it didn't take very long, just a few years before these dampers started leaking. The maintenance would refill them, but it got to a point where they could no longer refill them, and that's when Caltrans decided that they needed to be replaced. And like I mentioned, the Vincent Thomas has been in service for about 8 years. We haven't seen any leaks, so I would say the measures so far are effective. And again, like I said, it took less than 8 years before the original dampers started leaking. What was your other question? Monitoring. So monitoring, I mean, I don't think we have anything special for that other than, you know, these bridges have assigned inspection engineers that follow the federal requirements for the periodic inspection. And so that's essentially how we keep an eye on them.
Okay, thanks. Yeah, this aspect may be useful, interesting to explore further in the breakout sessions. We'll see where that discussion goes after lunch. From the floor, questions. Eduardo.
Thank you. So one is for Federico Scasciati, if how many Italian bridges are seismically instrumented? And the other one for Murat is on of bearings for the bridges. If they have been changed some criteria after the 2000 year.
Well, we have displacements as large as more than 1 meter, 1 meter to 1.2 meter displacements. Because Turkey's earthquakes are quite strong. And when it comes to near fault, unfortunately, we end up with very large displacements when it comes to isolation systems. And the recentering requirement, which is more stringent for bridges located near active faults, actually plays a good role in reducing the displacements of the isolation system. And that's the situation in Turkey now.
And so in Italy, we have sometimes we have seen, for example, some case studies. The problem is that when you have especially existing bridge, we don't have the possibility to have a great displacement because, for example, one of the case studies I show you, you have the two carriageway that are adjacent. So in this way, we have to connect the two carriageway because it's not possible because sometimes, especially for existing bridges that were not designed to high displacement in 1960, 1970. So it's not always possible to allow a great displacement. Okay.
But on seismic instrumentation, like how many of those are seismic?
Today, the most used is rubber bearings, for example, high damping rubber bearings. And in this case, we have that maximum displacement are regulated by device regulation. And in general, we have maximum displacement that are less than 1 meter. For example, the case studies we have seen 400 millimeter, 500, but if we have higher displacement, we have to control it.
And Federico, Eduardo was also asking about monitoring systems or measurement. Do you have many bridges with electronic monitoring systems for seismic displacement or acceleration?
With new regulation in Italy, we have the possibility to apply also monitoring system, but especially with the Polcevera collapse, these are for existing bridge. We don't have a lot of application in seismic isolated bridge, but in the recent years, we are improving. For example, the Sant'Onofrio Bridge, the last case studies, we have a project to apply a monitoring system, dynamic and static, because we have seen that the energy dissipation system was designed to perform differently in static and dynamic conditions. So the monitoring of this, the good behavior of the energy dissipation is important.
Thank you. Anyone else on the floor? Professor Marcus.
Thank you. So I want to return to this controversial concept of effective stiffness in seismic isolation. And maybe I want to ask Murat about this. So when you use sliding bearings, the picture is very clear. So we have a very short yield displacement, 1/4 of a millimeter, and then the bearing moves along its second slope, right? So the stiffness is W over R, and from this we get the isolation period, 2 pi square root of R over G. Right? So in sliding bearings, there is the second slope that does everything, right? So there is no need for effective stiffness, right? We agree on that. Because when the bridge moves 1/2 meter and the yield displacement is 1/4 of a millimeter, 1/4 of a millimeter to 1/2 meter is totally material. So K2, W over R is all it matters, right? Now, when you go to lead rubber bearings, the situation is very similar. We have maybe a little bigger yield displacement, let's say 2 centimeters, and this yield displacement comes from the yielding of the lead. And then the bridge moves again for 1/2 meter or even more so. So again, 2 centimeters compared to 1/2 meter are again immaterial. So in my mind, in seismic isolation, the only stiffness that matters when at periods and dynamic analysis is the second slope, which we know is 2 pi square root of R over G for isolation systems. So why messing with K effective?
Nikos, for an excellent question. I'll explain why we need to use that. Well, it depends on the characteristic strength of the isolator. Okay? Yes, you are right. You have the second stiffness or post-elastic stiffness K, talking about K2, but it also depends on the characteristic strength of the isolator. If it is very high in the case of rubber bearings, okay, it can be high, and also on the displacement as well, Also displacement matters. When you have very large displacements and you have very low characteristic strengths, you are right, okay? But when you have smaller displacements, large characteristic strengths, then you need to use the effective stiffness. So, and in the case of near-fault earthquakes, okay, you have done a lot of research in that, and I have read your papers and used them, okay? So this, for instance, in the case of near-fault earthquakes, the post-elastic stiffness controls the entire behavior. Why? Because the elastic part comes into the picture in maybe less than 1% of the time of all the movements, and that's the case, and you're right in that case. Okay, so we generalize it. We use this effective stiffness concept to cover everything, and that's the reason. Right? You're welcome.
I think we'll look for one more question if we have one on the floor before we end the session. Yes.
Thank you. A quick question for Murat. For the vertical ground motion component, what is the recommendation in the new guidelines?
Well, we have a spectrum for the vertical ground motions, okay, and we use that for scaling, okay, and we consider vertical ground motion effects in the analysis as well. Actually, if you're going to perform 3D analysis, we consider that, but the scaling is done based on the vertical spectrum. We have that, but I didn't introduce it. Have that. Well, we actually, what we do is that we have a lot of things there, which I didn't explain. In the case of the isolation devices, we allow for uplift up to 1 inch. Okay, we apply for uplift up to 1 inch. In the case of rubber bearings, Turkish design specs doesn't allow for tension. Okay, we don't allow that. Instead, we use a mechanism to allow for uplift. And uplift is not bad. Actually, Ian presented the bridge in the railway bridge in New Zealand, and that bridge is actually as isolated based on rocking. And it's not something bad. Some people are scared of uplift, but you can allow for it, especially when the bridge impacts, okay, the bearing impacts. What happens is that you have radiation waves through impact, and that dissipates extra energy. So it's not something bad.
Thank you. I'd like you all to join with me to thank our 3 speakers again one more time. Thank you.